Hi, in this video, we want to take a look at variable selection when we're performing regression analysis. Okay, so in real life, frequently we have a lot of predictor variables, and it works out that we don't usually want all of our predictor variables. Okay, the first thing we need to be mindful of is something where we call overfitting. What'll happen here is that if two variables, let's say they're like highly correlated together, but they're not perfectly correlated together. What'll happen is they're so close to each other that to get the model to fit as best as possible on the data, it will like inflate the coefficient of one, like it'll get too big, but then on the other one, it will make the other one like big and negative to counteract that inflation on the other one. So I've got two variables. They're highly correlated, they're predicting. Okay, so what can possibly happen, and the smaller the data you have, the more of a risk this is. This first one can get a large coefficient, too large, then the other one can get like a large negative coefficient to counteract the inflation on this one. And so what is happening is that the model is fitting to the data. All right, so one of the situations that we always have to be mindful of when we're doing regression is that our goal is to fit on the population, but we don't have direct information about the population. We have information from our sample. So we are fitting on our sample, and that is our proxy for the population. Well, whenever I fit on my sample, what I can do, there's always a gap. There's always a gap between our sample and our population. All right, there's always some kind of difference in there. All right, so if I put too much emphasis on my data, I can make a mistake in terms of the population because of that gap between the sample and the population. All right, so overfitting is the idea of our data really is over-representing itself in the model. The less data you have, the more risk you have. So the fewer observations you have, the more risk of overfitting you're into. Also, the more predictors you have, the more risk of overfitting you have. And that will be true in machine learning and data mining and linear regression, anything like that. Anytime you're doing supervised learning, you always have to be mindful. The more predictors I have, the more risk of overfitting I have. The fewer observations I have, the more risk of overfitting I have. Okay, so right now we're going to look at variable selection, and we're going to take two approaches. First one is exhaustive search. The idea is I go through and find every single possible subset of predictors I have, and then I build a model and I try to find the best model from all of those possible ones. So let's say that we've got 3 predictor variables. If I've got 3 predictor variables, then I have 8 subsets. All right, so 2 to the power of 3. Okay, I mean, that's a good number. All right, so let's say I have 4 predictor variables. Then I have 2 to the power of 4, which is 16 possible models. All right, that's not too bad as long as the data isn't big. Okay, okay. Now, what if I have 5 predictor variables? All right, well, that's 32 models. All right, well, I mean, that's a lot to slug through, but we can do it. All right, let's say we have 8 predictor variables. And 8's not a huge number, right? I mean, 8, we could easily have 8 in modern society. Well, that would be 256 models to have to go through. Okay, so that would be a lot. Do I want to go through and figure all this out? Which one's the best? No, I'm lazy. I don't want to do that. All right, so it grows very quickly. And because of this exponential growth on the number of models, this exhaustive search idea is a bad idea most of the time. If you're going to do it, you need to, either you're in a small data situation or you need to go get a sandwich while it computes. All right. Now, something else to always think about. Anytime I work on optimizing a model, I have to always expect the model to perform worse when I start working with real data, when I start making predictions. This is always true. The more I optimize, the more I can expect it to drop down in performance when I actually start predicting on real values. All right, so why is this? Let's think about sports for a moment. Let's think about the greatest college player in a given year for, let's say, college football, college basketball. Pick whichever one you want. I'm going to go with college football. The best college football player, when they get to the NFL, usually does not perform as well as they did, right? Okay, and they're usually not the top rookie play, if it's quarterbacks, the top college football player usually is not the top rookie quarterback. Well, why is that? Anytime that you optimize, you can expect things to drop down. Think about the MVP. If I have an MVP, and how do they do the following year after being the MVP? Are they the MVP again? Almost never. I mean, it happens once in a while, but almost never are they the MVP again. Why? Because it's kind of like there's this thing, other variables came into play that made them that good, that got them that good of stats. And so if you're really, if you're using skill and luck is going your way, luck, I'm not saying luck runs out, but your luck isn't going to be as good. The other variables involved are not going to be in sync more than likely, and it's going to drop down. Rookie of the year. How well does Rookie of the Year do his or her second year? Usually not as well as our first year. Why? Because things are pretty much optimum, and once things are not optimum, they can only go down. So expect that when we expect that same phenomenon when we're looking at regression models. All right, so let's go ahead and let's start working with the model. This is from the bridge data set from the textbook. And first thing we're going to do is we're going to load the data just like always. And now something I did, I went through and I found which variables were the most informative for this problem, and I ordered the columns in that manner. I got rid of an ID column. And the reason why I did this was just to, I like to do this for the purpose of teaching that it's easier to see trends and patterns when you organize your variables. In real life, I actually don't usually do this. Now here, I went ahead and ordered my ordered the rows so that like the target variable is the most important for the ordering, and then the most important predictor is the second most important in ordering. All right, so here's the full model. This is with everything with all my variables. Now here, you'll notice that from a previous video, we went through and we found the log transform was a good transform for these predictor variables and the target variable. So, since those were good predictors then, they're good predictors now. So I just go ahead and leave it. All right, now let's talk about exhaustive search. All right, first thing I want to say, this is usually a bad idea. This usually takes a long time, and we can expect the performance of the model to drop down because I'm going through so many iterations trying to find something good. When I pick the best, and it's the best possible one based off of the data, not the population, I can expect performance to decline. Be ready for that. This is something that bites a lot of people in the backside when they first start doing professional model building, because frankly, this is something that's not really talked about enough in this manner when we talk about, or when we're looking at like education and colleges and stuff like that, how they teach it. All right, so this function from the LEAPS package, and the LEAPS package is a good package to use. We'll go through all possible subsets of the predictor variables, and it's going to pick out the best models for the given number of predictors. So it's going to find for you the best 0 predictor model, which is the intercept, the best 1 predictor variable model, the best 2 predictor variable model, the best 3 predictor variable model, and so on. Okay, so what we do when we pass to the function is that we say like, what is the overall formula? Like, what's the big thing? So here, this is like the master formula. This is the full model. And what it's going to do, it's going to take the subset of these predictor variables and find exhaustively what looks like it's going to be the best model. Now, when I say the best model here, I'm saying the best model on the data. That does not mean it will be the best model on the population. All right, and let's go ahead and look at the summary. All right, the default setting for this function is to do exhaustive search. You can also do forward selection, backwards elimination, and stepwise selection, which we'll talk about in just a moment. All right, so here I can look down this list. So the part that's really important to us is this part. This part is just reminding us what we did. This is a force in, force out aspect. So if we wanted to force a variable in, force a variable out, that's important for when I'm in a situation that I need to keep a variable in. So it's only going to consider models that include that in there. All right, so if I look down here, this is normally what's the most important for us. We can see that the model with just one predictor variable had DWGS. So I'm going to call it dogs just because I think that's funny. So log dogs is the only variable in the one variable model. Okay. Now when I get to the two variable model, the best two variable model has log dogs and log spans. Okay. Now the best three variable model has dogs, spans, and cost. When I get to the best four variable model, it's dogs, span, cost, area. And then when I get to the five variable model, it's dog, span, cost, area, length. Now, something to pay attention to on this is that remember that I actually permuted around the order of the variables so that the most important ones were coming up first and least important ones on the right. And you can see that pattern in the stars here. All right, so what we want to do now, we want to plot the adjusted R squared for each of these. So if I run the summary on the output from the Leaps package and I extract just the adjusted R squared, we can see that our adjusted R squared for the one variable model is, the lowest. So it's like what, let's say 0.7, 0.69, something like that. Then up here we have better than 0.75, a little bit less than 0.76, then a little bit above 0.75, and about 0.75. All right, so one thing to realize that this is not really a wide range. I'm going from 0.7 to 0.76, so it's not a huge range. It looks like the three variable model is the best by this criterion. So remember, R squared, regular R squared does not take into account the number of predictor variables. Adjusted R squared does. One thing we always want to consider when I look at a model, if R squared and adjusted R squared are far apart, I have overfitting more than likely. All right, so here this is indicating that the three predictor model is probably like the best one to go with when we consider the risk of overfitting with the ability of the data to fit to the target variable. So here we're trying to balance. All right, I want all the predictors I can get without overfitting. So I'm in a Goldilocks problem. I want to fit the best model possible without overfitting. I don't want to underfit. I don't want to overfit. It's just like Goldilocks. And so here, this criterion says that 3 would be a good choice. But the difference between 2, 3, and 4 really is not that much. 2, 3, 4, 5 really is not that big of a difference. And here, this is another way to print this out, is to use from the subset function from the car package. And here, the thing that's nice about it is that it tries to put in an indication of which model it is. All right, so now on this next step, I'm going to go through, I'm going to build each of these models that were selected. And now what I'm going to do is I'm going to store all this in a list. Why am I doing this? All right, if you want to see like how you shouldn't do this, go to the textbooks website and get the example code for this. It's in chapter 7, the bridged asset example. And the author goes through and just iterates every single one individually. All right, that is going to put a lot of stuff on your R workspace. It's going to get cluttered. It's going to be disorganized. What I'm doing here is I'm going to store all of the models into one object, and in R, a collection of items that don't have that can have any type of structure are stored in a list. So I'm choosing a list. Lists are a very good way to keep your R workspace nice and organized. All right, so now something I did on this list was I went ahead and I named each model by the number of predictor variables. Why did I do that? It's just easier. I mean, I honestly, for the purpose of teaching, I don't care like which variables are in the 3 variable model. I just care that there are 3. Just going through it this way. All right, and I put it in the order numerically, 0 to 5. So this will be easier to just understand. And I just go through and I build it. So you'll notice that I take the linear model function. Oh, this is a mistake. Oh no, that's not a big deal. All right, so what this is doing, this overwrites LM full. All right, so I did not want that here. Okay. All right, everything works out for this example, but so you can see that I have an error in my code. I'm overriding LM full each time. It doesn't actually change the output on this example, but potentially it could have. And this is the full model. So like here, it's perfectly good, but these are bad. These are bad. I should get my hand slapped for that. All right, so now, after I have everything stored in the list, I can go ahead and just print the list out and I can see what I've got. So here, the 0 predictor model is just the intercept. The 1 predictor model is here. Gives us the coefficients. Coefficients from the 2 predictor model. Coefficients from the 3 predictor model. And all the way down to the coefficients of the full model. Okay. All right, so now one of the neat features about having everything in a list is that if I want to run a function on every single entry in that list, I can do that easy peasy lemon squeezy using an apply function. All right, so what I'm going to do, I'm going to use the lapply function. So lapply returns a list. So the L tells you that the output is a list. It's a list apply. I'm going to take the list of linear models I have that I just created, that we just looked at, and I'm going to run summary on each and every one of those models in that list. And so when I do that, I get this output. All right, so I can see that the intercept is statistically significant. All right, log dogs is statistically significant. All right, so dogs is still looking good. And now something that you need to pay attention to is you'll notice that the p-value changes a little bit. Now here's my standard error. And you'll notice that my standard error increased by a little bit. Okay, that is going to happen normally in multiple linear regression. What you can expect to see, the more that the variable, so if I add in a variable and it's correlated to variables that was already in the previous model, I can expect my standard error to increase. This is the variance inflation factor effect going on. So what's going on is that because of collinearity, because of correlation between the variables, what's happening is you can think of it as my variance is increasing, variance inflation factor. All right, so since it's increasing, like, you know, in statistics, for hypothesis testing, we don't like variance. We want variance to be small. All right, when I'm throwing in this correlation, it's harder for the algorithm to reliably estimate what's going on. And that's where this inflation factor comes from. All right, so now let's go to the next one. All right, so let's see. We have, let's say, about 0.27 becomes 0.36, 0.15 increases up to 0.21, then 0.09 increases to 0.11. All right, so, and now you can see that the standard error every single time increased because I added the log of C cost into there. So you'll notice that the p-value for the log of the span was less than 0.01, right? Less than 1%. Now, the p-value is greater than 8%. Quite a bit of an increase. You know, if I keep on going, I can see that, boom, increased. Now, this one didn't change by much. It did increase, but not by much. Here, increased by a little bit. Then here, this increase, that's a decent increase. Now let's go from the 4th to the 5th. That's a decent increase. All right, this is about the same as up here. That increased. All right, so what I want us to pay attention to right now, by throwing in more predictor variables, that can throw off my hypothesis testing. That's a problem. You know, so if I see that the variance inflation factor is coming into play, then I need to be concerned that I can't trust my hypothesis testing because I don't have reliable estimates of the standard error. Okay, so now, next thing we need to think about is trying to balance that fit in too many predictors Goldilocks problem. I don't want to overfit. I don't want to underfit. I want to be somewhere in the middle. All right, so here's our game plan. What we're going to do, we're going to consider how well does the model fit the data, but we're going to get hit with a penalty for every single predictor variable we have. Okay, so we're going to consider the fit mathematically, and then we're going to mathematically throw in a penalty for every predictor we have. Okay, the more penalties I have, so if I have a huge amount of penalties and I don't fit very well, it'll be very obvious that this isn't a good way to go. All right, so AIC is Akaiki's information criterion. And what we're going to do, we're going to take this information criterion for each of the models. All right, so what this is doing, this is basically taking the fit, how well it fits in terms of sum of squares error, and then I'm hitting with a penalty. And the more penalty I'm trying to balance these two, fit and having too many predictors. And so I can see, it goes like that. So what we want the least possible value. All right, so here, that is the most negative value we have. So we want the least value possible for our AIC. Okay, so negative 102.41. Now you'll notice that, a lot of these they're actually pretty tight with each other in this range. But that's consistent with what we looked at previously, right? Not surprising. So far, this is saying that 3 is ahead of the others, but it's not a heck of a lot ahead of the others. Now, other way to go is with the Bayesian information criterion. All right, so conceptually, it's the same thing that I'm going to consider the fit of the model, and I'm going to get hit with a penalty for every predictor I have. Okay, I'm going to try and balance the two. This is a Goldilocks problem. I don't want underfit. I don't want to overfit. The difference between these two information criterions, Akaikis and Bayesian, is that Bayesian has a stiffer penalty. And since it has a stiffer penalty, in this, if I'm using this criterion, I will frequently conclude I need to have fewer predictor variables in my model. All right, so let's take a look. All right, so I want the least possible value from the BIC, and we can see that's -97. All right, so we can see it by this criterion, the 2 predictor model is the model that we would want to use. But you can see once again, the 2 and 3 predictor models are pretty tight with each other. Okay, so AIC and BIC gives us a way of considering model fit and how many predictors we have for evaluating our model. There are tons and tons of different criterions. There are modifications to these 2 criterions. There are other various criterions. There's a million ways that you can go about this. Honestly, in real life, I just do AIC. I don't mess around with it too much. I found that BIC for real work pushes out too many variables. AIC I found is a good balance. There is a corrected AIC that is present in the textbook, but I felt like the code was just cumbersome, so I didn't want to include it in this video. Okay, it has better statistical properties than standard AIC, but in practice, I personally have not seen it make a difference. So I don't worry about it. But if your other professor in another class says it's the greatest thing since sliced bread, listen to your professor. Ignore me all you want. All right, so now, that's from Exhaustive Search. Another game plan we have is that I'm going to take the full model. And what I'm going to do, I'm going to look at all the possible, so I start out with 5 predictors. I'm going to go through and I'm going to look at, so pretend that each finger represents a predictor. I can build the model with these 4 predictors. I can build the model with these 4 predictors. I can build the model with these 4 predictors. I can build the model with these 4 predictors. I can build the model with these 4 predictors. Now I look and see which one of the 4 variable models is the best by the AIC or BIC. If that is an improvement over the 5 variable model, then I'm going to go ahead and keep that model. Okay, so now I've got 4, so now I've concluded this is my best 4 variable model. Now what I'm going to do is I've got 4 predictor variables. I'm going to go through, I'm going to look at this 3 variable model. I'm going to look at this 3 variable model, this 3 variable model, this 3 variable model, and I'm going to run AIC or BIC on them. And if that's an improvement, according to the criterion, now I'm going to I will accept that model as being my current model. And I'm going to repeat this until I no longer improve my AIC or my BIC, depending on which one I'm using. This is called backwards elimination because I start with a model and then I eliminate a predictor, and then I eliminate another predictor, then I eliminate another predictor until it's the best AIC I could possibly have. And so when I do this, in the stats package, it's the steps function, and the direction is backward. Now, the penalty for AIC is with k equals 2. That's going to be our penalty if I want to do AIC. If I want to do BIC, I take the log of the number of variables. Now, this output, what it does is it tells me, all right, it it starts with a full model, then it figures out which one to kick out, then it figures out which one to kick out next, it figures out which one to kick out next, and then it goes, hey, this is going to be my model. This is the one I'm going to go ahead and keep. Now here I'm doing the Bayesian information criterion. So this is the log of the number of observations. So here the difference between what we just looked at is that I have a steeper penalty. So what I'm expecting to see is that either the same number of predictors or maybe one or two fewer predictors. So it starts with a full model and it kicks one out so that I get this model. Then it kicks a variable out to give me this model. Then it kicks a variable out to give me this model. And this algorithm concludes off of this sequence that this is the best model by the BIC criterion. All right. Notice that previously there were 3 predictors when I did AIC. Now we have 2. All right. If I'm in a big data situation, I do not want to use exhaustive search and I do not want to use backwards elimination. Exhaustive search is much, much worse. When I have a lot of predictor variables, exhaustive search is a bad idea. Backwards elimination is a bad idea, but not as bad when I deal with big data because I start out using all of the possible variables. That's not feasible for a situation where I have a lot of data. Now, the other way I could go is do forward selection. Game plan is I start with the intercept model that has 0 predictors. Then I find the best variable to add to that. Then I find the best variable to add to that. Then I find the best variable to add to that until I no longer get an improvement by my criterion. Okay, so here, what we're going to do, I'm going to start with the intercept model and I'm going to add variables until I feel like, or until the criterion no longer improves. Once the criterion stops improving, I stop adding variables. So we start with the intercept and we check each of these. Which one gives me the best improvement? And is that actually an improvement over the intercept? If it's not an improvement, we don't include it. So then we see that adding dogs in there is an improvement. So the AIC goes from -41 to -95. All right, that's a decent improvement. Now, it goes through and it tries to find which of these variables is the best one to add on. Well, if we add on log spans, then our AIC goes from 95 to -95 to -102. That's an improvement. All right, so now it checks to see, should we add each of these on there? Well, we notice that if we add log of C cost, our AIC goes from 102.37 to 102.41. Not much of an improvement, but it is an improvement. Now, on the next step, it concludes that it's not going to actually be an improvement. So the algorithm stops and does not tack on the next variable. And here we get the output of our model. Now, we can repeat the same thing with BIC. Bayesian information criterion has a steeper penalty for adding a variable. So we expect to see either equal size variable or equal size model or smaller. Start with the intercept, add dogs, then we add log span, and now at this point, because the penalty is steeper than with AIC, the algorithm concludes that we will not get an improvement if we add on another variable. And this is it. All right, now, something that we always must be mindful of whenever we do optimization in statistics. Every time you do optimization, expect performance in real life to be less than what it looks like it will be on the data. There's always a gap between the sample and the population. If I optimize on the sample, I'm not necessarily optimizing on the population. So if I go through a variable selection process, the more models I try and experiment with, like with exhaustive search, the more models I built in the process, the more I can expect to have a drop in performance. Just be ready for that in real life. This will bite you in the backside like it did me if you are not mindful of this. All right, that's all I've got for you. Take care and goodbye.